Hey everyone, today we are going to be going over an important tool for circuit analysis, another important tool. So far we know KVL, KCL, and resistive circuits. This is going to be another thing in your toolbox, voltage dividers. So as I said last time when we talked about resistive circuits, when resistors are in series, then the voltage is divided between the two, the resistors, right? As I had explained in the resistive circuit portion. So right here we have resistor 1 and we have resistor 2. And we can actually find what the voltage is between here, and we call it V out because a lot of the times you'll have another load, let's just say like load or something like that, which could be a light bulb or something like that, or I don't know, a speaker or something like that. And basically, you will take a voltage from that is split between these two resistors and it will receive that voltage, right? So we're going to learn how to calculate this right here. Okay, so right now, and of course this is in relative to a specific ground that you choose, that you pick. So here are the equations, and we're going to derive them in a little bit, but it would be nice to commit these to memory. It would be very useful for you. There are more powerful um, there are more powerful methods than the voltage divider, but it's nice to have this handy because then you can conceptually visualize what it means to split voltage up. And if you have a very simple circuit like this, you can just use this rather than one of the more complicated but powerful methods. So let's go ahead and derive this. So first of all, it comes from Ohm's law. No surprise there. But we know that Ohm's law is V equals I R, and for emphasis, R equivalent, right? So it's the equivalent between these two resistors right here, okay? And so we can say that R equivalent is equal to R1 plus R2 as per the series configuration right here. So the current accordingly is going to be big V, right, over R equivalent, or V over R1 plus R2. Now we need to solve for the individual voltages, right? So remember that these individual voltages are dependent on their respective resistor, and we know that in series the current is the same, right? And so we have V1 and V2 is equal to I and R2, like so. Now we have the equation for I, and that is this guy right here. So all we have to do is plug in I into each one of these, and we get, which is exactly what we have here. And the general formula is the number of resistors all totaled up. So this is all R equivalent, and then over under the specifics, the Ri. Okay, because it's just a fraction, right? We're getting a fraction of this circuit, of this configuration's voltage dissipated from each resistor. Okay. Now let's go ahead and solve a problem. So, using the voltage divider, we want to find V1 individually and V2 individually. So, we'll just do a simple plug and chug. V1 is R1 over R1 plus R2 times V. And what do we get? We get 4 over 10 times 10, which is V1 is 4 volts. So that means there is a voltage drop of 4 volts here. Okay, voltage drop of 4 volts. Okay, and so because we said it was a fraction, technically you could solve for this voltage right here without using a voltage divider. It's just going to be 6 volts, because if 4 volts are dissipated up here, then that means there's going to be 6 volts left for this resistor to dissipate. So this guy right here is going to be 6 volts. Okay? But for the sake of completeness, we're going to do V2 equals 6 over 10 times 10 equals 6 volts. Okay, for this next problem, it's a little more complicated, but not too much. Just break this up into parts. So first of all, we want to find V1, right? So that means we're going to have a voltage divider between this guy right here and this configuration right here, okay? So what are we going to do? Well, we're going to find the equivalent of these resistors right here. Okay, so step 1, find, and we can call this R1, R2, R3, and R4. So find R2, 3, 4. So we're gonna find R3, 4 first, which is just 2 plus 4 equals 6, and R2, 3, 4 is equal to 6 over 2 equals 3 ohms. And then we can find the voltage divider between step 2, the voltage divider between R1 and R2, 3, 4. So we get that V1 is equal to 2 ohms over 2 plus 3 times 8. Excuse me. And we get 3.2 volts. So V1 is equal to 3.2 volts. And now we have to find V2. So how do we find V2? Well, we're going to have to find the voltage right here, which is just going to be 8 minus 3.2, or you can find V234, which is going to be 3 over 2 plus 3 times 8, which will equal 4.8 volts. So then that means right here, this configuration is seeing this 4.8 volts, and it's going to be dissipated accordingly. Now remember what I said, that amongst this nodes, in a node, the voltage is distributed, well, not distributed, it's just the same. So right here, we have a voltage drop of 4.8 volts, and then a voltage drop here of 4.8 volts. So then that means in step 3, if we want to find the voltage 2, actually we should call it the voltage 4 because we named it R4, so I'll just go ahead and change it right here. The voltage 4 is going to be equal to, so we're going to have to do a voltage divider between these two resistors, 2 and 4. So what we're going to do is that the voltage 4 is going to be 4 over 2 plus 4 times the voltage that it sees, which is 4.8 volts. 4.8 volts. And that is going to equal 3.2 volts. Okay? So, as you can see here, it seems like both the answers are the same, and it does make sense, right? So let's think about this. Let's find actually V3. Okay, V3 is going to be 2 over 6 times 4.8, and that is going to equal 1.6 volts. So if we plug in, let's just say 1.6 volts here, 3.2 volts here, 4.8 volts here, and 3.2 volts here. Well, as we can see here, 1.6 and 3.2, they add up to 4.8. So we know that right here, 4.8 and 4.8 are the same. So this entire configuration right here sees 4.8 volts. And this configuration right here, or just this resistor, sees 3.2 volts. And 3.2 plus 4.8 equals 8 volts total, which corresponds to the fact that this right here is 0 volts or ground. So that is how you use a voltage divider.